Very good morning, students. In the previous lecture, we have discussed about the Faraday's laws of electromagnetic induction and self-inductance mutual index. Okay, so in the today lecture, we have discussed about the going to discuss about the inductance in series, inductance in parallel. Okay, so before going to topic, so let me again recap the Faraday's laws of electromagnetic induction. Okay, and self-inductance, mutual inductance. So they are the two laws of the Faraday's laws of electromagnetic induction. One is that the first law and second law. The first law. Okay, so first law states that so we are having the two laws. One is the first law and is the second law. Okay, so both are based upon the electromagnetic. Okay, so which are relating the electromagnetic. Okay, in the first law states that when the magnetic flux linking a conductor or coil changes an EMF is induced. Okay, so first law is the states. So just a moment. Okay, so the first law. Okay, the first law states that when the magnetic flux linking, okay, flux linkage a conductor, coil or coil changes when the magnetic flux linking of a coil or conductor changes an EMF. Okay, so an EMF is induced in it. Okay, so an EMF is induced in it is called the first law. Okay, so first law states that when the magnetic flux linkage of a conductor or coil is changes, okay, so an EMF is induced, that is the magnetic. Okay, so first law. Okay, so Faraday's first law. The second law. Okay, so in the second law, so in the second law, the magnitude of the induced EMF. Okay, so the magnitude of the induced EMF, the magnitude of the induced EMF in a coil. Okay, the magnitude of induced EMF in a coil is equal to the rate of change of magnetic flux linkages in a coil is equal to the is equal to the rate of change. Okay, so here's a rate of change, rate of change of magnetic flux, rate of change of magnetic flux linkages. Okay, so here's the first law. So both these Faraday's laws both are related to electromagnet. So electromagnet is nothing but which should give the supply. Okay, so here these there are two types of magnets, right? Is now which if you are having the permanent magnets and the temperament. So ferromagnets, diaphragm, so that's the difference. So just we take class weight based on the magnetic property. So permanent magnet per temperament. So permanent magnet which will induce the magnetic flux continuously. Okay, this will induce come, and these electromagnets. Okay, so electromagnets with the one coil, and this will be supplied. Okay, so supplied by the DC source or AC source, then it will act as a magnetic. Okay, so then induce the magnetic field, so then it will act as a magnet. So this type of called as the electron. So here based upon the that, okay, so EMF induced, that is the electromotive force. Okay, so they are the two laws. Okay, first law, that is the Faraday's laws, in the first law, when the magnetic flux linkages of a conductor, okay, so here's the conductor or coil. So it's a coil or conductor is changes and EMF is induced. Okay, is magnetic flux linkages which is the producing by the conductor or coil. If the flux linkages changes, okay, an EMF is induced. Okay, so an EMF induced in it. So here the EMF is induced in it. Then it is the first law. Okay, next the second law, the magnitude of the induced EMF. Okay, so magnitude of the induced EMF in a coil. Okay, so in the first law that is, so EMF is induced in it. Okay, the second law, the whatever the EMF is induced, okay, the magnitude of the induced EMF in a coil is equal to the, okay, whichever is the induced EMF is equal to the rate of change of magnetic flux. Okay, is equal to the rate of change of magnetic flux. Okay, rate of change of magnetic flux. Okay, so we can write that is the E is equal to, okay, E is equal to rate of change of magnetic flux, rate of change of magnetic flux. Okay, so he can we can write, so here is a N is the number of turns, rate of change of magnetic flux. So if it's the one solenoid conductor and the north pole south pole has the number of turns, so we can say the number of turns of conductor with the N, the magnetic flux which is indexing. Okay, so this will indicate by the phi 1 and this is the magnetic flux one. Okay, so induced EMF due to the flux induced EMF, then some magnetic flux that will indicating with the phi 2. Okay, rate of change. Okay, so rate of change of magnetic flux, so that is the N, the number of conductors. So rate of change, that is the number of turns, that are minus. Okay, so next N I1. So with respect to the rate of change, that is the time. So we can take N is a common and we can write phi 2 minus phi 1 by T. Okay, so E is equal to N of phi 2 minus phi 1 by. Okay, so here we can write this one equation, that is a E is equal to N d phi by dt. Okay, so in the differential form, okay, so this is for the in differential form, we can write that is the N E is equal to N d phi by dt volts. Okay, so in usual, okay, so here is the in usual from the Lenz law. Okay, so from the Lenz law, so the current conductor, okay, so the current flowing through the conductor and EMF which is induced the opposite sign of it. Okay, so opposite direction of the current flow, so induced EMF is opposite direction of the from. Okay, so for that one E is equal to minus N d phi by dt. Okay, from the lens up, the current induced in the conductor is the opposite direction of the EMF. Okay, that's why that's the minus sign we can take. Okay, so that E is equal to minus N into d phi by dt. Okay, this is the Faraday's second law. Okay, this is about the Faraday's second law. So this is what we have discussed in the previous lecture. Now we will go for the what is meant by self-inductance, mutual inductance in detail. So so the okay, so EMF induced are the two types. Okay, so EMF is from Faraday's law. Okay, so from the Faraday's laws, there are the two types of induced EMF types. Okay, the first one is statistical. Okay, statistically induced EMF. Okay, statically induced EMF. Another type, dynamical. Okay, so dynamically induced EMF and statistically induced. So in the statistically induced EMF, they are having the types. The first one is the self-induced EMF, and second one is the mutually induced EMF. Okay, so we'll talk about this one. So statistical means will having the only stationary parts. Okay, there is no rotational parts. So it will having the one if solenoids and contacts, and which are having the battery source. Okay, then it will having there is no rotational part. If coming to the dynamically, so here is the it will having the one magnetic electromagnet and the conductors in the rotation. Okay, that is the dynamically induced EMF. Here we talk about the self-induced EMF. Okay, so here the self-induced EMF. So first we'll talk about self-induced EMF. The EMF induced in a coil. Okay, so this says that the EMF, the EMF induced in a coil, the EMF induced in a coil due to due to the change due to the change of its own, okay, due to the change of its own magnetic flux. Okay, due to change its magnetic flux linked with it. Okay, due to change its magnetic flux linked with it. It's called self-induced. So here so here we are having the one coil which are having the here it will put, and here the you will having the source they are connected, and the magnetic field. Okay, so here the magnetic field is there. Okay, so here the magnetic field induced by this coil is there. Okay, so this the magnetic field is induced by. If the magnetic field, okay, so due to the magnetic field, the EMF, okay, so the EMF induced in a coil due to the change of its own magnet. Okay, here this is a magnet, so here is a conductor. So if variation in this one, okay, so magnetic fields change of its own magnetic fields is linked with it. Okay, the EMF induced in a coil due to the change of its own magnetic field. Okay, so whatever the magnetic field there, it's due to the change in this the here EMF is induced. Okay, so here in this coil an EMF. Okay, so one is the supplied voltage and another is the induced EMF. Okay, if another EMF is induced in this coil, okay, that is the self-induced EMF. Okay, that is called as a self-induced EMF. Next we'll talk about the mutually induced EMF. Okay, so in the mutually induced EMF, the EMF, okay, the EMF induced in a coil, okay, in a coil due to the changing current. Okay, due to the changing current in the neighboring coil, okay, due to the changing of neighboring coil. That is called as a mutual inductance. So here we can take, so here is the one coil we are having the mag, that is which is connected to the source, okay, and here we are having the another coil, okay, so which are connected here, and we are placing with the 1 galvanometer, okay, to show the, okay, so if due to this, okay, so here it will be induced in the magnetic field, right? So which are connecting the voltage source, it causes the production of magnetic field, okay. This magnetic field flux is linked with this one, okay. So this is the coil 1, is the coil 2. So due to the magnetic field of the coil 1, is EMF is induced in it, okay, and due to the induced EMF in the coil 2, okay, if that is the, if EMF induced, that is the, okay, the EMF induced in a coil due to the changing the current in the neighboring coil, okay, if EMF is there, okay, so EMF so here also this is causes the again production of the EMF, okay, so from 1 to 2 it will, then 2 to 1 also EMF will be changes, okay, that is called as a mutual inductance. Okay, so that will be called as a mutual index. The EMF induced in a coil due to the changing current in the neighboring coil is called as the mutual inductance. Okay, so this is about the self and mutual inductance. Okay, so there is a representation for self-induced EMF, mutual induced EMF. Okay, continue to the self-inductance, mutual inductance. Okay, now we'll talk about the, what are the formulas, okay. So if it is he the self inductance, okay, so what are the factors will affect in inductance, okay, so how it will be represented, okay, that will be talk about. So in the property of the coil, okay, so in the self in, that is the inductance, okay, so in the inductance the property of the coil that opposes any change in the amount of current flowing through it, that's called as the inductance. So inductance is nothing but, so inductance is nothing but the property of the opposing of the any changes in the amount of current flowing through it, okay, the property of a coil that opposes, okay, the property, right, that opposes any changes, okay, that opposes any changes in the amount of current flowing, in the amount of current flowing, amount of current flowing through it, is called as a inductance. Okay, that we can say that the property of the which oppose the flow of change, okay, so if amount of current flowing through it, okay, so it will be opposite which oppose the changes in the current, okay, that we can say that is the inductance. Okay, so the inductance we can indicate with the letter L. So units are the henries, so we can indicate that is a capital H. So here let we take the expression for the inductance, self inductance. Okay, so here first we are taking the one, coil and having the number of turns, and here is a n is having the, so one coil is having the n number of turns. Okay, emf is induced that by coil, that is E. Okay, so from the self-induced emf, okay, so magnetic field is induced, the change, okay, due to that we can say that is n d phi by dt. Okay, so here the current, okay, so whichever causes the current flow through this, okay, magnetic field. So here the magnetic flux is due to the change in the current. So the magnetic flux, the magnetic flux is due to change, okay, due to current through coil, okay, due to current in the coil. So that is, we can say that is the magnetic field, okay, so which is directly proportional to the rate of change. The magnetic flux linkages will proportional to the, okay, so magnetic flux is directly proportional to the current flow, is that is the E is equal to, okay, so is directly proportional to the di by dt, that is the emf, that is the emf induced directly proportional to the current, okay, so along with the current. So here we can, E is equal to direct proportional di by dt, so here E is equal to di by dt, okay. The proportional constant we are writing as the L which is causes, okay, opposite flow of changes, that is the E is equal to L di by dt. Okay, is the where L is constant caused the self inductance. It is the self inductance. So it is called as a self inductance of the coil. The units we can mention, that is a volts. Okay, so L, the for L it will having the induct units Henry. Here E is equal to nothing but V. Okay. So that is, there is nothing but self-inductance E is equal to N d phi by dt. Okay, that is self-inductance. So here is the expression for the inductance. Okay, the magnetic flux is directly proportional to the current changes. Okay, that is the E is equal to E direct proportional to di by dt. So we can write that is a E is equal to, here is a proposed constant considering the L. So that is a self-inductance di by dt is equal to L di by dt. Next, we will take the mutual inductance. Okay, so we'll talk about mutual inductance. So in the mutual inductance, we are considering the two coils. Okay, so here we're considering the two coils. Okay, so here is the two coils. The magnetic field around this one is the phi 1. Okay, phi 1 2. So which is the in between the two magnetic field. So A and B. A is the coil and B is the, so in between the magnetic field, that is the causes both, that is the phi 1 2. So the two coils are arranged that the change of current is one causes the an emf to be induced in the other side, okay, the rate current. Okay, so here's the two coils were arranged in the changes, okay, arranged in that change of a current in the one coil, okay, change of current in the one coil causes the emf induced in the other coil. Okay, if the flux is variation in the first one, okay, causes the emf induced in the second. Okay, the magnetic field of the A is varied, okay, then emf field is induced in the B. Okay, if magnetic field of the B is varied. Okay, then EMF induced in the B. So that is called as a mutual inductance. So here we can write mutual induced EMF of the coil B. Okay, so mutual induced EMF of the coil B is directly proportional to the rate of change of current in coil A. Okay, rate of change of current in coil A, that is a mutual inductance. We can indicate the EM is equal to, sorry, E directly proportional to di1 by dt. Okay, so EM is equal to M di1 by dt. Okay, so here I1 is nothing but rate of change of current variation. Okay, so magnetic field. So the current variation is the A is causes the production of EMF in the B. Okay, so B. So EMF induced in the magnetic field, the B is equal to EM. So indicating the mutual inductance, the EM direct proportional to the di1 by dt. Here is the EM is equal to M di1 by dt. So here we can write EM. So we'll take the expression for the EM. EM is equal to M di1 by dt. Okay, so that is equal to, we can write M I1. Okay, then we are wearing, that is the, so here M into I, that is the magnetic field. So in terms of the variations, we can also write this is the coupled coil, right? So we can write this is the N2. Okay, so causes N2 d12 by dt. Okay, so both are equal. So if you take the mutual inductance di by dt of N2 flux 1 2. Okay, so by equating the two expression. Okay, so equation 1, equation 2, if you equating the both equations, mi1 is equal to n2 512. Okay, so m is equal to n2 512 by I1. So we can also in the terms of reluctance. Okay, so we can also write in terms of reluctance, we can write m is equal to, okay, n1 n2 by reluctance. Okay, so we can also write this m is equal to n1 n2 by reluctance. That is a number of turns of the n1 n2. Okay, so coil 1 coil 2 by reluctance. So okay, so that is the reluctance comes to the another part. Okay, so we can just here we can take the, this is the mutual inductance, m is equal to n2 by n2 into 512 by I1. So 512 the variations of the magnetic field due to the both. Okay, so this is about the mutual inductance. Okay, so here we are saying that the rate of change of current is causes the flux EMF induced in the coil B. Okay, so here that is equal B direct proportional rate of current coil is causes the B, a coil A. Okay, so EM directly proportional to dI1 by dt. So mutual inductance EM is equal to M by L. Okay, so from that we are writing the for last. Okay, M is equal to N2 512 by I1. Okay, so this is about the mutual inductance. Now we'll talk about the, so if series, okay, so inductance are in series, so what happened? Okay, so if inductance are in series, okay, so how we can say that if both inductance and series are both inductance and parallel. Okay, so why we talk about self inductance, mutual inductance means if the resistors, okay, so if the, in case of the resistors, so there is no, here will only, it will produce in the only heat, okay, but due to the heat there is no variations in the current. Okay, so if the parallel and series, then only variation in the voltage and current only. But if coming to the inductors, okay, so if it is connected in parallel, so this will be causes in the EMF productions. Okay, this will be affected the voltage supplied in. Okay, if the connected in series, so it will causes the another thing. Okay, so that's why we have to know about the what is by self inductance, mutual. Okay, because we are connecting the two coils, right? So it will cause the EMF productions. So for that one we are going, we have studied about the self inductance, mutual inductance. Okay, we have to know about the concept of the self inductance and mutual inductance, right? Now we'll talk about, okay, so if inductors are in series, okay, so what are the possibility of the connections? So here we can say that, so if, okay, so if taken positive, so if resistor we are taken the positive negative, okay, so connections, okay, so aiding. So here there are two possibility of the connections in the series of the inductor. Okay, so one is called as a series aiding. Okay, so one is called as a series aiding. So one is called as a series aiding. Okay, so next one is a series opposing. So here's how we are connecting. Okay, that is the most important, because in the resistor if you connected the reverse positive negative, it will be different. Okay, but in the terms of the inductor, okay, so this will causes more variations in the inductor. Okay, the mutual inductance, okay, so because here if you take north pole and south pole, okay, if the connections is there, okay, so if we vary the north pole to south pole, south pole to north pole, then the magnetic field wind, okay, so the magnetic field produced by the coil, that will vary. Okay, that's why we have to be careful while connecting the series connections of these. Okay, that will comes the two types. Okay, so series aiding and series opposing, because it will variations. So series aiding, series opposing, there are the two types. So here the series aiding means, so the magnetic field of the two coils. Okay, so if we take, so one here we indicate with the north, we can say, okay, so same direction. Okay, it, if the indicate with the uh, connections will same, okay, then this type of thing. So here the both due to this connection the magnetic field is increases, then it is called as the series ending. Okay, in the series opposing due to the variation. Okay, so here due to the variations of this one, okay, the mutual in the magnetic field will be decreased. Okay, so this is called as a series opposing. Okay, so this is called as a series opposing. So in the series ending the magnetic field will increase. Okay, the magnetic field increases. In the series opposing the magnetic field will be decreases. Okay, so for series aiding, okay, so series aiding, the formula is LT is equal to L1 plus L2 of 2M. Okay, L1, that is a L1 L2 and mutual inductance in between. Okay, it is 2M. in the series opposing. Okay, so in the series opposing, the formula is LT is equal to L1 plus L2 minus 2M. Okay, that is the simple. So L1 L2, if it is series adding, that is the L1 plus L2 plus 2M. If series opposing means the mutual inductance will be, the magnetic field reduced, right? That is L1 plus L2 minus 2M. Okay, that is the this. So how it is came, that is the L1 L2 2M, L1 L2 minus 2M. Okay, that will be discussed in the next further session. Okay, just in the series connection there are the two types. One is the series aiding, another is the series opposition. Okay, so for series aiding, the magnetic field will be increases. In the series opposing, the magnetic field will be reduced. For series aiding, the formula's total inductance LT is equal to L1 plus L2 plus 2M. For series opposing, LT is equal to L1 plus L2 minus 2M. Okay, so that is about the series of. If parallel, okay, so if inductors are connected in parallel, so in the parallel connection, okay, uh, here there is no problem. Okay, the magnetic field will be different. Okay, so here the same as that of the resistance. So total inductance is equal to, so total inductance is equal to 1 by LT plus 1 by L1 1 by L2. Okay, total inductance in the circuit, that is a 1 by LT is equal to 1 by L1 1 by L2 1 by L3, like this. Okay, so we can discuss about the in detail what is the parallel connection formula, what is came. Okay, how series connection, that derivation. Okay, that will part in the discuss in the later section. Okay, there are the some problems where you can deal with the series opposing, series aiding and parallel circuit. Okay, thank you. This is the end of the session.